everyone, and welcome to Keeping Tabs on Chemistry. In this video, we are going to be talking about equilibrium. So far we have represented chemical equations as only occurring in one direction. So in the production of water, we've got H2 and O2 reacting to produce water molecules. Now, we could also say that two water molecules can decompose into H2 and O2. So many chemical reactions are actually reversible. So instead of using a one-sided arrow, we can use a double-sided arrow, right? This can be represented bunch of different ways. It could be full-headed arrows, half arrows, but the general idea is you're going to see an arrow pointing one way and an arrow pointing the other way. So there are tons of acceptable ways to represent reversible reactions. Now, reversible reactions reach a state of what's called chemical equilibrium between the forward and the reverse reactions. We're going to talk about what that means. So, the state in which forward and reverse reactions balance each other because they take place at equal rates is called chemical equilibrium. Right? So, when we are having equal rates of the forward and the reverse reaction. So, although a chemical reaction may be in equilibrium, the products and the reactants are continually changing because a chemical equilibrium is a dynamic process. So what that means is if you were to use a strobe light, right, looking at this reaction, right, every flash of that strobe, you would see the same amounts of products and reactants, but that doesn't mean that it's standing still. Right? There's motion in between. There's still a forward reaction and a reverse reaction. The reactants are reacting, the products are reacting. It's just that we don't see any change in the relative amounts of them, right? So when the strobe light is off, we don't see the change happening. All we see is during the flash. So equilibrium is governed by something called Le Chatelier's principle. So Le Chatelier's principle states that if a stress is applied to a system at equilibrium, the system shifts in the direction that relieves the stress. So what happens is we can have a reaction that's at its equilibrium. It's got equal forward and reverse reaction. The strobe lights go in. We don't see any differences. But if I change something, if I apply what's called a stress, then I'm going to see a shift either towards the products or towards the reactants. So we would say, either shifting right towards the products or shifting left towards the reactants. What that means is now when I flash my strobe light, I see a different amount of reactant or product. If I've shifted right, I now see more product in my strobe. If I've shifted left, I now see more reactant in my strobe. Right? Once it reestablishes its equilibrium, right? Once it relieves its stress, it's going to go back to every strobe light looking the same. It's just a different same. So shifting equilibrium means that reaction is going to react in one direction for a moment before the rates of the forward and the reverse reactions equal each other one again. So by shifting equilibrium, we create more products by using up reactants or vice versa. So it's like a game of tug of war. Right. I'm going to either pull it to the right or pull it to the left, but then I'm going to equal out again. So my flag is in a different position, but it's not moving again. Okay, so factors that affect equilibrium. The first factor is going to be concentration. So just like we learned with reaction rates, increasing concentration increases the number of collisions of those molecules. So an increase on one side of the reaction will push the reaction towards the opposite side. So if I increase, right, my amount of reactant. So if I add reactant, the forward reaction is going to occur more, right? More collisions of the reactant molecules means the forward reaction happens. So this is going to push the reaction towards the products, a shift to the right, the opposite side. Now, if I added product, the reverse reaction is going to occur more, which means I'm going to push my reaction towards the left, the opposite side normally did. Now, a decrease on one side, so removal of a chemical, will push the reaction to replace what was taken away on the same side. So removing product means I'm going to shift right to make more product. Removing reactant means I'm going to shift left to produce more reactant. Right? So same idea, when I'm shifting right towards the product, I'm going to see more product in my equilibrium than I had originally. Now, it's important to remember with equilibrium, this is a shift. Okay, it's not that I'm making all product now. It's just that my equilibrium, when I balance my forward and reverse again, right, that strobe light shows more products than reactants from when it was originally at equilibrium. It is at a new equilibrium. Right? Now, the removal of a chemical is actually what chemical companies or pharmaceutical companies do in order to produce their product or their item, whatever it is. So say a drug. So I'm going to remove, all right, my acetaminophen as I make it. That's going to push my reaction to keep making more acetaminophen. If I didn't take any out, then I would just have one set amount of acetaminophen and I would never make any more, even though I have reactants available to do that.
Okay, so practice number 1. Which direction will equilibrium shift? So the first one says add H2. Now looking at this, H2 is on the left. So if I'm adding it, I'm going to shift to the opposite side. So in this case, that is going to be the right. The next one is to add H2O. No, H2O is on the right. So when I add it, it shifts to the opposite side, which in this case is the left. Now the last one's a little different. It's asking remove O2. Now O2 is on the left, but by removing it, I'm going to shift to replace it. So it goes to the same side. So if it's on the left, it's going to shift to the left. All right, so the last factor that's going to affect equilibrium is temperature. So we're going to think about temperature as you would any other reactant, considering whether the reaction is endo or exothermic, and that is going to make a difference. So we're going to treat them separately. So we're going to start with endothermic. In an endothermic reaction, heat is required, which means that heat is going to be a reactant. So if I represent it in an equation with delta H, the delta H is going to go with the reactants because that heat is required with the reactants in order for the reaction to occur. So in terms of equilibrium, right, adding heat will push the reaction towards the products, right? So when I'm adding heat, I shift to the opposite side, to the right. Same is true if I'm removing heat, I'll push it to the same side, to the left, to replace that heat. Now this only works for endothermic where that delta H is on the left. Right? With exothermic, heat is produced. That means that heat is a product. So my delta H now is on the right side. Right? It is coming out. The heat is being released in this reaction. So adding heat will push the reaction towards now the reactants on the opposite side. Removing the heat will shift to replace it. So it's the same concept with concentration. Adding is opposite, removing is the same, but you have to be careful because endothermic, the delta H is on the left, exothermic, the delta H is on the right. So here is practice number 2, asking once again, which direction will equilibrium shift? So in the top one, I can tell that this is an endothermic reaction because my delta H is on the left side with my reactants. So increasing temperature will shift to the opposite side, the right. Decreasing will shift to replace it on the left. Now on the bottom, I've got the combustion of methane, right? So in this combustion reaction, I am releasing heat. It is a product. This is an exothermic reaction. So increasing temperature will shift to the opposite side, the left in this case. Now, I've told you about the factors that do affect equilibrium. There are some factors that do not affect equilibrium. So, we've learned that concentration is the major factor that affects equilibrium. Temperature can also affect it. There are substances that do not have a concentration. Remember, concentration is based on the relative amount of solute and solution. Um, or solute and solvent really. So pure solids and liquids do not affect equilibrium because they do not have a concentration. So any amount of solid or liquid available to a reaction will be used up until it is gone. Right? There's no balancing with our strobe light here. So if you dump water into your reaction, it's not actually going to change your equilibrium at all. Right? It's used up until it's gone if that's part of the reaction. Now, only gases and solutions will change equilibrium because only gases and solutions have a concentration. Now, we haven't talked about gases yet this year. We're going to revisit that on our unit on gases. But for now, if you see a gas or solution and you're changing that particular part, that will shift your equilibrium. Changing solids and liquids will not cause a shift. And that concludes my lesson on equilibrium.